Today I'm delighted to be here to present my research entitled Toward Human-Aware Autonomous Cyber Defense, Cognitive Psychological Intelligence for Adaptive Security Operations. In today's talk, I will talk about the human-aware autonomous cyber defense as a new direction for cybersecurity, where defense systems not only aware of the network and attacks, but also aware of the human analyst operations. I should highlight here in cybersecurity center, especially SOC or Security Operations Center, we increasingly rely on AI-driven automation to detect threats, response, and any activity we want to do. But these systems, these days, consider this assumption human analyst is always performing well and optimally. In reality, I should highlight, analysts operate under significant cognitive stress that especially faces during the major cyber incident. In this today discussion and today presentation, I want to bring this question: if cybersecurity system adapt to the cognitive state of the human, especially security analysts, what consequence we will have and what pros
Hey,
and
sorry,
cons?
Abbas.
Yes. Can you hear me, Tal?
Are you showing your slides? Are you moving your slides? Because
No,
yes, I can hear you, but your slides is not moving.
Okay. No, it's just introduction about my presentation, then I will go for
Oh,
movement. And yeah,
sorry.
just
I thought,
for
okay,
okay,
my
no
bad.
worries. Before deep dive to this presentation, I want to bring this question about this presentation. If a cybersecurity system adapt to the cognitive state of the human, what will be the consequence? Let's get started. Regarding the agenda of this
Can you
presentation,
reshare your screen, Abbas? Can you reshare your slides?
sure. It goes.
Good. Yeah, it works. Great. Please continue.
Okay, all right. Let me briefly outline the structure of this presentation. First, we'll start with discuss about why autonomous cybersecurity systems must be human aware. And then we will explain the limitation of the current security operations and consider why existing system ignore the important factor as a human state toward the cognitive situation. On top of that, we will introduce our proposed framework as a cognitive psychological synchronization, which integrate psychological sensing and cognitive decision modeling. And then we will deep dive into the experimental evaluation and also demonstration of the improvement to our operational stability. And finally, we wrap up this session with consider human-aware autonomous cyber defense and its implication and pros and cons toward our digital world. Let's get started. As you know, in cybersecurity operations, SOC centers, increasingly they are integrated with autonomous and AI-driven solutions. For example, these days we can mention in SOC pipeline, we are utilizing AI-based threat detection mechanism, autonomous incident response, machine speed response, and on top of that, continuous threat hunting and monitoring systems. However, these systems just consider the automation and ignore human decision making as for example, stress or cognitive conditions any human or cybersecurity analyst they are facing. In practice, I should highlight is a person in security center try to interpret alerts, consider some defensive strategy, try to prioritize incident, escalate critical threats, and other tasks. So if this person faced with a lot of alerts or sensitive or critical alerts to make a decision, so it provides a lot of difficulty for providing a solid decision-making process. Consider an example. For example, when a ransomware attack is spreading across a network, for example, in the hospital, the SOC analyst quickly should make a decision about the current situation. For example, should the system be isolated from the server and other network infrastructure, or should the patient system, for example, in the hospital, remain online, or it was a false positive? To respond to this question, we need to have a provide security decision making in the SOC. So if the analyst faced with a lot of tension, stress that provide or degrade the quality of the decision making process. In this research, we want to show not only the human should be considered as a part of security analyst in the autonomous cybersecurity defense mechanism, but also consider this element as a critical or principal rule of designing any cyber security strategy. If you want to provide more details in this regard, consider the cognitive stress as a major impact as a directly on the performance of the analyst. Under a stress condition, no one can deny we face with several limitations in terms of slower decision making, increased error rate, and also more false positive or escalation. So most of the cybersecurity tools at this stage try to consider the technical part, not only, for example, human state. Try to consider or monitor traffic, system health, device behavior, and also threat indicators. But completely at this stage, try to ignore human cognitive capacity or capability. Based on the previous example I bring here, imagine in the SOC, we are receiving a considerable number of the alerts in the runtime. Even if the detection mechanism are perfect, but analysts still may face with some challenges and facing with the poor decision due to alert fatigue and cognitive overhead. Here, exactly, we are facing with the true bottleneck as a human cognitive. And in this today presentation, we want to show how we can integrate human cognitive conditions into the system, decision-making system in cybersecurity as a part of autonomous solution. And another thing I should highlight in this slide, as you can see, we are facing with a new attack surface based on this vulnerability we can take. So this type of attack is considered denial of decision or DOD in direction of the autonomous cybersecurity that should be measured based on the integration of the human cognitive situation and also autonomous cybersecurity implementation. In our next slide, we can see the missing piece of the autonomous cybersecurity. Based on this matrix, simply if we consider the machine state, just we are focusing on the, as I already mentioned, in network traffic, system health, threat indicators, and device behavior. On top of that, in the human state, we are completely ignore some cognitive load, decision fatigue, analyst capacity, and also human stress. If I want to provide a solid example here, if the system just monitor network traffic, we are ignoring cognitive load. If the system monitor health, we are ignoring decision-making process. If the system monitor threat indicators during threat detection and threat hunting mechanism, we are ignoring the analyst stress. All these decision process, all these activities result automation without human awareness. So as a part of this research, this gap is bring this motivation for us to deep dive and provide a solid framework. Because in the modern aviation systems, we can see the cockpit monitor pilot, for example, workload and fatigue. But in cybersecurity, we still assume the analysts operate independently and under pressure. Although this person is the human, it faced with a lot of challenges and difficulties in the hectic situation. We need to, when we want to provide an autonomous solution, we need to consider these criteria in the runtime. Let's turn to the scientific point of our work and the research. If we consider the psychological feature that would be part of the human journey, it's provides some multimodal psychological sensing, cognitive state in the real world and decision policy, and toward having human on the loop. On top of that, in the cybersecurity side, especially autonomous cyber decision, as a part of machine, we are utilizing some, for example, removing manual operations toward autonomy. In these two domains, we need to provide a bridge to fill this gap, to provide a cognitive psychological synchronization. That's a part of our framework, try to cover this gap via building this bridge, because our goal here is enable cybersecurity defense systems considering the human state. We want to have a system not only infer analyze cognitive stress in the real world, but also integrate stress into decision policy in critical tasks in autonomous cyber defense. So, in other words, we want to build a system differently depending on the situation as cybersecurity analysts face in the runtime, make a decision and provide a recommendation for that state we are taking in the right direction or not. Let's consider more details in this field. In this slide, we can see our core idea, how machine and infrastructure can be considered as a direction, and human biological capacity provides some feature for us. Intersection and overlap between these two domains we called as a cognitive psychological synchronization. That would be part of our proposed framework. We want to create a closed loop between psychology and cybersecurity decision. That system can provide some capability for us, like detect stress from psychological signals, update cognitive model based on the analyst situation, adjust decision policy, adapt the cybersecurity action to create human-aware defense system, especially adaptive defense systems. Let's get into it. In this slide, we can see our proposed framework to support this research. First of all, let me introduce all these steps. Here we have a cybersecurity operations center environment. A cybersecurity analyst is working in this component to tracking the system behavior, checking dashboards based on the received alerts. And after that, we have another component based on the wearable devices the analyst used to detect some, for example, human state. Based on the sensor and actuator we connected to the analyst, we are collecting some psychological signals in terms of ECG signals, EDA, and respiration due to doing this research. And in the next component, we are deep dive into signal processing to extract some contextual information based on the collected signal. And then we are utilizing some machine learning and deep learning models to classify state of the analyst in terms of stress or normal situation. And then we are passing this information into a stress state component to provide some information. And then we are move this information to the most important part of this framework as a cognitive agent. This agent try to simulate the human behavior and utilizing some reasoning during making decision about the situation that analysts in the first step do. And in the action module, we have this capability and this chance to consider what was our consequence, what was the decision making in which situation. We need to monitor this decision. We need to escalate. We need to, for example, redistribute the task to another cybersecurity analyst while that person can do without any stress. So if we want to uh, briefly wrap up this framework, first, we are collecting some wearable sensor to collect some psychological information. Then goes the signal to the signal pre-processing and feature extraction. Next, machine learning try to estimate stress probability. Then we synchronize this information with cognitive agent model as a cognitive AI. It's provide a lot of information for us to detect this information. And finally, the system try to detect adaptive defense. So we start from psychology condition, goes to our cognition, and then via cyber defense, we are doing this loop. In the following slide, for each component, we will deep dive and provide more details and examples and how this framework can connect it to each phrase and provide some input for next step to provide decision-making process in the autonomous cybersecurity defensive or offensive systems. Let's get into multimodal psychological intelligence. In this work, we consider three types of psychological signals. First, ECG signals. It tries to measure heart rate. And no one can deny the heart rate is strongly correlated with stress and cognitive workload. When the heart rate will increase, and it has a direct relation with the stress and cognitive workload. The second signal we are considering is EDA to measure electrodermal activities. And another signal we are working with that it's emotional, it's related to the respiration which try to change under stress and other human condition we can consider. By combining these three type of signal, we try to provide a robust estimate of the cognitive stress when the cybersecurity analyst in the runtime facing with that. If I want to bring example here, consider this situation. During simulated cyber incident, we observe increase the heart rate, and it provides a lot of information for us. Not only cybersecurity analysts face with some stress, but also we can check the higher skin condition and movement of the wrist, for example, because it's working with some devices like, for example, mouse. Via these movement and via this heart rate, we can provide this information. Maybe that person is facing with a lot of stress and tension during decision making. It directly decrease the quality of the decision in that center. So these signals we are utilizing in our work try to evaluate a stress level. And in our work, we utilize some mathematical proof and notation to justify this theoretical concept to our proposed framework. Another component, when we are getting some information about the signals, we need to do signal processing and also utilizing some machine learning algorithm to classify between stress and non-stress. In this situation, we try to utilize some models. In our research, we utilize some classification models like SVM, support vector machine, random forest, XGBoost, deep neural networks, and also a hybrid model combination DNN plus XGBoost to provide high performance metric in terms of accuracy and AUC that demonstrate to us the threat stress detection can reliably be inferred from some psychological signal to make a decision about the analyst was in a stress or relaxed situation. One of the most important component we have during this framework is related to the cognitive psychological synchronization. This component try to integrate estimate the stress into decision policy. The idea is straightforward because when the stress increase, the system modify utility of different actions. For example, if the analyst is highly stressed, the system prefer safer action. We define these actions while considering monitoring instead of the escalation, automated assistance, workload distribution, and also considering some normal situation when the analyst can work perfectly. Because all these conditions help us to reduce the risk of the stress when cybersecurity analyst wants to provide or help to the autonomous systems when we have a person on the loop. In the following slide, we will provide more details about this condition. So in this slide, we can see one of the challenges we tackle in this research. As you can see, the signal, especially psychological signal, are noisy. And to address these problems or to tackle this situation, we apply temporal smoothing with the cognitive context. It helps us to prevent rapid fluctuation when we are facing with this signal in the decision. You can see how this raw signal is mapped to the probability of the stress because utilizing temporal reasoner try to combine three items for us. First of all, psychological evidence, then cognitive confidence, and later historical context. It not only help us to provide a meticulous information, but also it's improved the policy of the stability because we consider several situations for cognitive systems to monitor, to escalate, to redistribute the task, and also provide some recommendation for cybersecurity in that loop. Let's look at the pounding heart of the proposed framework, the cognitive agent. In this work, to simulate analyst behavior, we use a cognitive architecture called as a SPDI-IBL. This model represents a decision-making process using memory retrieval and reinforcement learning to provide some stress effect regarding the cognitive parameters. And here we can see some performance metric or parameter as a higher stress increase when decision noise, and memory retrieval becomes less reliability and decision latency. So considering this noise, memory latency, and retrieval latency provide this capability for a cognitive agent to think like a human and behave like a human. And in terms of speedy IBL, I should mention it's a cognitive decision-making model works based on the incident-based learning or IBL. And it why utilize this theory to design and simulate some human things, human works, human making decision, and using past experience to provide the active learning via having this memory. In this module, when consider the stress and pass to this one, it try to simulate the cybersecurity analysis. And in the next module, when we will get this information, we have this capability to make a decision, the cybersecurity analyst, how did this workflow. Let's look at that. In this slide, we can see several adaptive action we are considering in our work as a assist, monitor, redistribute, and escalate. The key idea here is that the system doesn't respond in the same way. Instead, we try to adapt its behavior based on the analyst's cognitive stress level. On the left side of this diagram, we can see four possibilities. When the stress is low, the system either monitor environment or try to assist analysts by providing some cognitive support, such as action or summarize alerts based on the received alerts. And when the stress becomes moderate, the system begins redistribute tasks, try to consider other cybersecurity analysts and offloading some alerts between other person or provide investigation to other analysts until keep the automation process in the autonomous cyber defense. And finally, I should highlight when the stress becomes high, the system escalate incident to supervisor. And because we want to ensure about the critical decision are made reliably and without any, for example, human error or integrated with the stress. So as the stress increase, the system shifts from the assistance to the workload distribution and then eventually toward escalation. Because we want to helping and maintain stable and reliable security operations. In this slide, we summarize all closed loop, or we summarize our closed loop architecture, because the process, as you can see, start from the human analyst, then we consider the multimodal sensing, then we are utilizing some, for example, stress estimation. In this regard, we use signal processing, machine learning algorithms to do this estimation. And later, while considering cyber psychological synchronization layer, we simulate human behavior and pass this information to the cognitive agent to make a decision about the initial decision that made via cybersecurity analyst. Especially in this dashboard adaptive action, we have this capability to judge about the initial performance and initial task has been done via cybersecurity analyst. So these actions try to reduce analyst workload in the real world situation, which fit from the initial sensing step toward making decision and having human in the loop to address these lag and problems. The question which raised here, how we evaluate the proposed framework. In this research, first we utilize VSAT dataset. This dataset is provide psychological stress data, as we can see in this stage. And second, we are utilizing cybersecurity dataset. It contains realistic cyber threat scenario. For example, here we consider DOS, DDoS, and also brute force attack in this data set. And we created a simulate SOC environment where analysts try to map, for example, the stress condition toward the cyber threats. And via this combination in mapping, we have a solid data to test and evaluate the performance metric of the proposed framework in terms of considering, for example, machine learning, like accuracy, precision, recall during a stress detection, and then the performance of the cognitive AI agent while considering noise, for example, retrieval information, and also some other items, because it's allow us to evaluate stress adaptive policies when we are up and running their proposed framework. This slide presents the distribution of the psychological features via VSAT data set. At the top, we can see the distribution of the key features derived from ECG, EDA, and respiration signal toward baseline as a normal situation and a stress. For example, when the EDA features tend to the increase during the stress, to the higher psychological arousal, we try to get some information about the cognitive load. And via the implementation, some machine learning algorithms and hybrid model as a DNN and XGBoost, the best performance metric, it's meet here via DNN and XGBoost model. We got the accuracy of the 90% and AUC 96%. This result show that our multimodal psychological features allow to have a reliable stress detection as a part of the proposed framework, which is a key component for our human-aware cyber defense, especially when the cognitive agent try to simulate this behavior from the initial information. In this slide, we can see the evaluation of the analyst performance in three conditions as a low stress, medium stress, and high stress. On the low stress, the analyst perform well based on the decision latency, retrieval success rate, and also error rate. We can see the realistic and optimum situation. As the stress increase into the moderate level, we begin to see the performance degradation. The decision latency increase, as you can see. The retrieval success rate is decreased from 93.5, it decreased to 87.2. And also the error rate is increased. And under the highest stress situation, we can see the impact becomes more significant in terms of decision latency, retrieval success rate, and also error rate. These slide provide this understanding for us. The key is increasing stress directly degrades the decision performance in cybersecurity operation. And I should highlight here, our speedy-able cognitive agent reproduce the human behavior because it allows the system to anticipate performance decline and trigger adaptive intervention when it's necessary. And In this slide, we can see the cost of this cognitive overload. This slide tries to highlight the operational cost of the cognitive overload in cybersecurity environment. As the stress increases from the low to high, as we observe, there are several measurable performance has been impacted in terms of decision latency, error rate, and also retrieval success. So I should highlight here, without intervention in the human becomes the system's greatest vulnerability. In today's lecture, we mentioned we are facing with the new attack surface. This vulnerability can provide this opportunity without having a solid threat. We are exploit a new type of attack as a denial of decision or DOD. So this new direction of the research in cybersecurity can provide this understanding for us in addition to the network infrastructure or system, like for example, we need to consider human state when we have an expert in the loop during the decision making process. So this slide illustrates how our system close the loop through the adaptive situation. In first step, we are utilizing the machine severity and, for example, IoT alerts or anything. Then we can utilize the human cognitive stress. And next step, via some CPS, cyber physical psychological data set, we evaluate that one, and then we try to utilize utility aware because we want to have a reason and a chain of thought when we simulate the human behavior. And then via the action center, we have this capability to judge about the cybersecurity analyst situation. It faced with stress during the decision making or no. And in last step, we try to simulate the environment to situation when autonomous system can work during decision making, during defense strategy without any law, without any flaw, and also limitation in terms of the human error. In this slide, we can see operational impact of our cyber psychological framework. In the green items, we can see the, for example, monitor and then assist situation. In the blue color, we can see redistribution threshold, and on top of that, we can see the escalation situation. We are analyzing the cybersecurity time frame. When a person is up and running in the center, we can track his or her behavior during the runtime and see their decision when the alert can see and can erase to make sure that person work optimally and in realistic situation. We provide some baseline model as a rule-based baseline and cyber psychological framework that utilize SPDI to consider this performing as a false escalation, accuracy, and real-time visibility. To propose a framework can track the behavior of the analyst near to the runtime. And the execution time here is less than 300 milliseconds to provide a back and forth between cybersecurity analyst and the sender receive alerts. And also in this slide, we can see some situation. We were in the, for example, stress situation or monitor situation when the system consider this concern, maybe the person that works under stress start to monitor and then try to detect the area of the stress. It provides enhanced probability we are utilizing during the confidence of the ground truths of in our work. And in this part of the chart, we can see the cognitive agent decision making. It's completely overlap and aligned with those timestamp the cybersecurity analyst faced with the stress, and we can see this escalation that would be necessary. And finally, we can see the SPDIable simulation. That's a part of our dashboard and action we need to take and policy we need to implement and add during the up and running of the proposed framework. So this slide we want to present a broader vision of the future roadmap of this research. Beyond the threat detection, autonomous threat detection, we need to consider some more feature direction as a multi-analyst and federated biological modeling, agentic AI governance to provide some policy, and finally provide a human AI co-adaptation, not only consider the infrastructure part of the autonomous cybersecurity solution, but also human cognitive. So as a final point here, I can highlight traditional autonomous cyber defense just focus on understanding threat vulnerabilities and try to remove the situation they exploit. However, this research we show not only this part is necessary, but also we need to have a realistic situation to consider analyst state as a human. The future security operations center need to create a workflow that considering human cognitive adaptivity and also psychological signals. While we can see in the modern uh, aviation system, already we have this implementation. So as a conclusion, this part of the presentation, I should mention in this today presentation, we introduced cognitive psychological synchronization framework that enable real-time human-aware security operation by integrating psychological sensing and adaptive cyber defense. Then we mentioned to the multimodal sensing approach, considering three types of signal as a ECG, EDA, and respiration, and get high performance metric for stress detection. And third, we utilize synchronizing cognitive state with decision policy to reduce false escalation, operational error, and improving stability. And finally, our results show the proficiency of this work and also quality of the implementation in terms of high performance metric. As a final work, final everyone for your, I would thank you to my colleague, Professor Karimpour and Professor Halabi during part of this journey of their research, and I am happy to take any question.